What skills do graduate engineers need to learn? This presentation is going to be in general terms and refers to almost any engineering discipline. Towards the end, I'll comment about robotics and mechatronics. Well, what do you learn at university? Here's a student. At university, you learn the theories. When you start work, you learn the practical stuff. But what is this practical stuff? Here's a competency definition used by Engineers Australia for the Chartered Engineering status. That's a Stage 2 competency. It's just one of 16. Generating value communication. These competencies have been used for about 20 years as a proxy for an understanding of engineering practice. And they were synthesized on the basis of comments from engineers, surveys, and academic research, which aimed to synthesize the requirements for engineers at graduation and then later seeking chartered status after 4 to 5 years of practice. In the last 20 years at the University of Western Australia and a few other places around the world, there's been a lot of interest in researching what engineering is really all about. Here are some of the results. Well, here's a surprising result, because here we're talking about graduate engineers just a few months out in their first jobs. And you'll notice that very few of them are doing anything substantial in terms of technical work. Most of them, between 1 and 10% of the time, is spent on technical work. And what is really interesting here is that the vast majority of them are spending a lot of time on social interactions, searching for information. And although there's some discipline variations, for example, in petroleum and environmental engineering, graduates do rather more technical work, the pattern is largely similar. And it's really interesting that the amount of time spent on social interactions, communication, and so on and so forth is very little different from that of experienced engineers, say 3 to 20 years of experience. From this research, I have synthesized this understanding of engineering practice. Essentially, it's two threads. Across the top, we have essentially desk work, paperwork if you like, identifying client and society needs, conceiving future solutions, and predicting the future. And at the bottom, we have the investment decision and then delivering that predicted future. And the green arrow on the left-hand side here is the process of learning from that experience of delivery to better identify client and society needs. So this understanding of engineering practice can then be overlaid with what students learn at universities. Essentially, these little dotted white areas are what students learn in their university studies. Here ticked in green. Now, if we think about it, very little is learned in university about really conceiving future solutions. Design is a very small part of the courses. Almost nothing is learned about delivering practical solutions, and nothing is learned about identifying client and society needs. There's no opportunities for feedback, and investment decisions are a topic that is offloaded to the business school. So it's not surprising, therefore, that engineers tend to see all of this stuff, which is most of what they do, as not real engineering. They classify it as non-technical work. And this leads to many misconceptions among engineers in general, but particularly amongst novice engineers, that we're talking about graduates through the first 3 or 4 years of their practice. Here's another way to describe engineering practice. In this term, this on the basis of skills and knowledge. So in this diagram, we have 3 pillars on which engineering practice is supported. On the right-hand side, we see engineering and business science. That's the stuff you learn at university. On the left, we see perception skills, visual perception, reading, and listening. And in the back, half hidden, is this idea of tacit ingenuity. This is the stuff that enables you to come up with practical solutions in engineering. And it is hardly mentioned at all in university. There's very few opportunities to develop that capability. Now, on those three pillars rest technical and financial foresight and planning, critical aspect of engineering practice. It's not really mentioned in universities except for maybe a token course in project management. And above them, technical collaboration performances. And sitting on top, there is value creation. This is the value that emerges from engineering practice. And I've portrayed that as three, if you like, cups of tea. My wife loves cups of tea, by the way. Client satisfaction, that's really important because satisfied clients pay their bills. Achievement satisfaction, best summed up in the words of an engineer who said, I took my granddaughter to see one of the ships that we built, and I pointed out to her, you see that funny little yellow thing that sticks out on the right hand side? That was the bit that I designed. And then at the back, of course, reputation, and it's through reputation that you get ongoing work. So if we look at the middle bit, the technical collaboration performances, technical foresight and planning, we find that that expands into something like this. We have, in essence, 5 major technical collaboration performances. What we call discovery learning, which is shared learning when neither side really knows what's needed. Teaching, engineers do a lot of teaching. Technical collaboration, project, which is really all about uncertainty management, and multi-stakeholder negotiation. These are complex socio-technical performances, which are not mentioned, I should say hardly mentioned at all in universities, but are critical in terms of effective engineering practice. So I want to start by mapping the gaps. Competencies, often broken down into knowledge, skills, and attitudes, start at the, if you like, represent the starting point for mapping gaps, if you like, capability gaps between engineering graduates and competent engineers. But there's 2 more that are seldom mentioned, which I think are very important: expectations and values. By values in this case, I mean instinctive preferences, and we'll see what that means in a little while. And I want to expand on those last 2 just a little bit. Graduates have important and well-defined expectations of what they think engineering work is really all about. They think that it's going to largely require independent thinking, that is, you have to be self-sufficient, that it's going to be technical, that the requirements are going to be tightly defined in unambiguous terms, complete information will be provided, and above all, decision-making will be logical. In terms of instinctive preferences or values, there's a distinct preference for solo performance. You know, what I do is what's important. Important communication has to be in writing, and above all, what's important is technical competence. Now, of course, as many of you would appreciate, these conflict sharply with the realities of engineering practice. Those conflicts are going to become more apparent as we go through this presentation. Why is it important that we mention this up front? Well, this is a picture of water drops on water-repellent soil, which I have in my garden in Perth in Western Australia in the summertime. In the heat bakes wax onto the surface of the sand grains that make up most of our soil. And those 2 water drops have been sitting on this soil surface for around about 4 hours, and none of that water has soaked in. Now, the point I'm making here is that engineering graduates with mistaken expectations develop what I call learning repellent minds. And that is because they have certain expectations, for example, for technical work. When it comes to learning what they see as non-technical stuff, like, for example, project management, contract management, how to handle difficult relationships at work, they say this is not relevant. This has nothing to do with engineering. This is not the engineering that I was trained to learn. And that's the challenge that we face, because graduates are very unwilling to engage in learning what they see is non-technical stuff that has nothing to do with what they think is real engineering. Before going on, I want to perhaps digress a little bit and expand on what we mean by knowledge, because we can't really talk about knowledge gaps unless we understand what is meant by knowledge. So we have explicit written knowledge, that's the stuff in books, that's what you learn at university and you have to reproduce in exams. Implicit knowledge, it's unwritten but it could be written. For example, where is the toilet? Procedural knowledge, which is basically how to engage in practiced sequences of actions. Tacit knowledge, knowledge that you're unaware of, like how to ride a bike. Embodied knowledge, which is associated with a particular artifact. For example, if you consider a road, embedded in the road is an awful lot of knowledge about how to build roads, but you need to be an engineer, a road design expert, to appreciate it. And contextual knowledge is knowledge that depends on the situation. For example, light switches go up to switch on things in America, where they go down to switch on things in many other countries, including Australia. Skills are these two in the middle: procedural knowledge, practiced sequences of actions, and tacit knowledge particularly. So let's talk about explicit knowledge gaps. Well, for a start, the standards. And for example, in mechatronic engineering, recently we identified around about 75 standards which are relevant. Why are standards important? Because they embody experience. They embody the knowledge that engineers have learned over many years. And consequently, you need that knowledge in order to practice effectively. Procedures, how to buy things, what's involved in estimating, tender preparation, regulatory approvals, contracts, occupational health and safety, and environmental parameters. Suppliers, crucial information about where you get stuff in order to build things. Another one, value generation, how you generate commercial value from your engineering practice. And I talk in terms of value creation, delivery, protection. Sustainability, what are the emission reduction requirements? If you want to make the world a better place, how do you advocate for improvements when a lot of people say it's less expensive to do what we've done before? The critical importance of human behavior when it comes to sustainability, and what are the commercial opportunities? Simple things like, what does it cost to employ an engineer? What does it cost to hire labor? What is the difference between indirect costs and on costs, operating costs, capital costs, and so on? These are all topics which are not covered at all in universities. Risks and uncertainties, stakeholders, the issue of people have diverse interpretations. Everybody understands something different with the same set of words, and the same set of words can mean different things at different times and different places. Financial risks, asset management, control measures, insurance, the practical significance of ethical behavior. Leadership depends on referent power, and referent power in turn depends on the perception of ethical behavior. As one engineer said to me in an interview, you know, engineering, especially specialized fields, are very small communities, and if you stuff up in Port Hedland tomorrow, they'll know about it in Norway today. And then intellectual property, patents, an enormous source of valuable design information, but most students hardly know about them. How you protect your intellectual property, how you search for new ideas, transport regulations, how you move things, occupational health and safety regulations, planning regulations, what you can do in particular places and what you can't, employment laws, regulations, contracts, budget, and cost control. Now, of course, nobody learns all that stuff, not even a small fraction of it, even in a whole career lifetime. In practice, knowledge in engineering is actually distributed in the minds of the participants, and many of them are outside the firm, people like suppliers, financiers, customers, clients. And the process of learning to practice engineering is also the process of learning how to access this social network of knowledge. We don't learn it all. Instead, we know people who know it. And engineers spend a lot of their time engaging people to contribute knowledge and skills, expertise, through collaboration. I'm going to come back to that in a minute. When we talk about skill gaps, well, the first and most important is perception skills. Listening. Engineers spend 25% of the time listening. They spend a lot of time seeing, reading documents, and reading people is incredibly important. Reading people's emotions when they're cooperative and when they're not. Writing skills, emails and documentation. Time management. Now, I mentioned just a couple of moments ago this idea of distributed expertise, the idea that knowledge is actually situated in the minds of people who are in the firm and the organization and outside. So in order to access that knowledge, we need collaboration. And here is one of the largest barriers for young engineers. If you like, it's like a mindset, what I call a value or instinctive preference. Young engineers essentially learn over 20 years of schooling and university education that what you do as an individual is important. And yet in engineering practice, it's what you do with other people that's important. You only succeed in engineering by helping others succeed in a great collaborative performance involving maybe hundreds, maybe thousands, maybe tens of thousands of people. And in our research, we've identified systematic performances. These are performances that engineers learn and that young engineers could learn if only they knew how to do it in the first place. The first one is discovery learning. How you learn from other people when maybe even the person that has the expertise doesn't actually understand what you're looking for, and maybe you both learn something along the way. But there's definitely a technique that you can use for that to be far more effective than simply a simple teaching exercise. Informal teaching. Engineers can only achieve things through the hands of other people, and consequently they need to spend a lot of time teaching other people what needs to happen when they themselves actually don't know enough to completely specify what needs to happen. Again, it's a collaborative exercise. But like any learning, you have to think about objectives, what you want people to learn, their language. There's no point in trying to teach people if you don't understand the language that they use. You need to understand what they already know, their interests, expectations, and you need to figure out how you're going to know that they've actually learned what they need to learn. Technical coordination. We know that this takes up around 30 to 35% of the time of engineers across all disciplines. It means it involves choosing the right people to do things, making things happen, planning, negotiation and organizing it, monitoring what's actually happening, and handover at the end. Project management, which is essentially the task of managing uncertainty, and most of that uncertainty arises from interpretation differences. Understanding technical specifications, frequently ignored in most project management courses, and the idea of teaching written documents. Project management relies on written information, and very few people understand what's involved in getting people to acquire that knowledge so that they can take the right decisions at the appropriate times. Finally, multi-stakeholder negotiations. Really interesting that technical problem solving, often acknowledged as the heart of engineering, is often a negotiation exercise. It's challenging enough to get people to even agree that there is a problem, what the problem is, and then, of course, lots of people want to dodge responsibility for having to do work to solve the problem. So gaining alignment on objectives and resolving these differences is essentially a negotiation exercise. Sometimes finding the technical solution is the easiest part. Workplace learning. So how can students, graduates, how can they learn all this stuff? Well, obviously the supervisor is the key. Mentors, very helpful. Short courses can fill in many gaps. Many companies have graduate development programs. And in the process of acquiring chartered status, one would hope that engineers have a lot of learning on the way. What I want to introduce briefly here is an idea that we've come up with recently. When my colleagues and I helped Engineers Australia develop the current set of competencies that define chartered status, that is the Stage 2 professional engineering competencies in Engineers Australia, we recognized that there was very little learning material that applicants for the process could use to acquire the skills and knowledge expected of them. And so, in revisiting this issue last year, I realized that what was really needed was a definition of the kind of performances that one could expect of novice engineers. Um, you have to translate competencies into performances because competencies, as I explained before, really only mean something if you're already a competent engineer. They're such brief definitions that without that knowledge of what engineering entails, they're very easily misunderstood. Hence the need to break them down and present them as a set of performances. And I'm going to give an example in a moment. These performances are categorized into the first year and then subsequent years. They're grouped by Engineers Australia competency definitions, and they provide a means of recording when the mentor or the supervisor recognizes that the performance has been achieved at a professional standard. And finally, there's lots of suggestions for improvement in performance, training, references and sources, and so on. So here's an example, just a quick example from the document, which has recently been officially recognized by Engineers Australia as encapsulating the expected performance requirements for mechatronic engineers who are applying for chartered status. So this is section 1, ethics. And here's the example. On year 1, you see that a young engineer would be expected to describe situations that more experienced people have encountered when ethical issues, dishonesty or conflicts of interest were apparent to them. And then second, would be able to describe restrictions on the distribution of information and explain the reasons for those restrictions, and so on. So there's something like 20 pages of these performances grouped by competency, and I'm quite happy to make a copy of that document available to anyone who's interested. And in conjunction with that, The Making of an Expert Engineer, the book that I released 6 years ago, describes engineering practice and what engineers do and the knowledge that's used by expert engineers. And I have a new book coming out, or I should mention this Guide for Value Creation, a big gap that we've noticed in all engineers, how to produce commercial value effectively from their work. Most engineers have only the very simplistic ideas of how to create value, and this leads to lots of frustrations between engineers and their employers. I want to finish by by mentioning the kind of gaps that I have noticed in my career in robotics. These are the kinds of things that young engineers need to learn an awful lot about after graduation. Definitely one is integration, how to interface software to electronics, to sensors, to amplifiers, actuators, to machines and processes, and the commercial components and subsystems that you can buy in the market that make that so much easier than it used to be. Reliability and quality assurance. Many engineers conflate or confuse these two concepts. Specialized components, crucially important in robotics. Where to find specialized bearings, gear drives, motors, reliable cabling and connectors. Nearly all the failures that I've ever encountered in my robotics work start with cabling and connectors. Sensor subsystems, software, and also, of course, the design techniques for selecting and implementing all these things. So that's what I have to offer. Happy to answer questions, and one day I look forward to meeting you in person.